back. In this video lecture, we will discuss about magnetic fields, and in particular, we'll discuss about force on a current element. In the previous video lecture, we have seen what actually is a magnetic field. Prior to MSc1, we have discussed about capacitors. In the SLT21, we have discussed about magnetic fields. And in this video lecture, I hope that by the completion of this video lecture, you'll be able to develop expressions for force on moving charge, and you might be able to say me what actually is a current element and how to represent that. So prior to this one, I will start with quick review of magnetic force on a moving charge. We have seen that if there is a magnetic field, and if I take a charge and move it with a velocity of v bar in this magnetic field, then this charge will experience a magnetic force which is given by qv star v bar. Now let us suppose if this charge is a differential charge or a small element, or maybe which is not clear, then we will represent it using dq, which is a charge element. So this is charge element. Okay, so a charge element dq, if it is considered, then this expression will result in df, because differential force is equal to differential charge into these remain the same. So this is the expression for differential force on a charge element. This is a charge element. If you want force, you should integrate it over the entire, either it is a surface or volume or a length, you are supposed to integrate it to obtain the force. Now, key things to remember in this particular equation, if you carefully see, F is equal to Q V bar star V bar, right? That I have already mentioned, right? This is the movement of velocity, the charge, and this is the direction of B. The force which is developed on this charge, it will be perpendicular to both magnetic field and also the direction of movement of the charge. Try to remember this one. The force is perpendicular to both the velocity of the charge and also the magnetic field. And this magnitude is given by cross product of V and B. So if you want the magnitude, what you can write? F is equal to, if I want the magnitude, I'll take it as QVB sine theta, where theta is the angle between V and B. And the maximum value of F comes when this theta value is 90 degrees. Okay. Normally theta value will be somewhere between 0 to 180 degrees. Okay. So to get a maximum value of F, you should ensure that both this charge is moving at right angles to magnetic fields. If it is moving along the magnetic field, then the field will be 0. And the direction of this force is given by right hand rule. Okay. The force relationship above is in the form of a vector product, and the direction will be given by right hand rule. Okay. So this is the representation of if I represent right hand rule. So if this right hand, thumb, index finger and middle finger, so this right hand rule will give you the direction of the force which is experienced by the charge when it is moving in electric field. The details which we will discuss in the next class regarding the right hand rule and the left hand rule and right hand thumb rule. But as of now, what is another term? Lorentz force, which is commonly heard in this magnetic forces. Lorentz force, as already told, any stationary charge, it develops electric field, right? So any moving charge, moving charge is nothing but current, right? If a charge is moving, it is resulting in a current. Any moving charge can develop electric field and magnetic field also. Okay, this is called as a Lorentz force. So Lorentz force exerted, it is the force exerted on a charged particle Q moving with the velocity v through an electric field and magnetic fields. Okay, so the entire electromagnetic force on the charged particle when it is moving in an electric field and the magnetic field, it is called as force, Lorentz force. So it is named after the Dutch physicist Enrique Lorentz and is given by, we know that if E is the electric field, the force when a charge is moving in electric field is F is equal to QU, and if it is a magnetic field, right, this is magnetic force, this is electric force. So this is Lorentz force. This is contributed by the electric field, this is contributed by the magnetic fields. And in this one, the force direction is perpendicular to the direction of velocity and direction of magnetic field, whereas here the force is in line with the electric field, direction of electric fields. Now, we will see the force on a differential element when we are going through the force on a differential element. Let's have a quick review of the formula. Now let us suppose there is a charge which is moving in this fashion with a velocity of v. Okay, there is a charge which is moving in this fashion with a velocity v is the velocity. Okay, now the distance traveled by this charge in time duration of dt is given by, this is the displacement, a simple physics formula. Displacement is equal to velocity into time. Now I am considering only a small time, so dt, so the displacement would also be differential. This is the expression. Now consider a charge which is characterized by a volume charge density rho, which is spread over a volume dv. So we know the differential charge is given by dq is equal to rho into dv, because q is equal to, we know, right? So what I am doing, differential charge is nothing but rho into dv. Now if the volume is considered to be the one which is crossed by this charge in this direction, so what I will do is nothing but I will separate it as ds into dv. This is surface area, this is length. If I multiply these two, I will get differential volume. Okay, so what I am doing now, dq is nothing but rho into ds into dv. So we will do one more thing. What we have already got is dq is equal to rho into ds into dv, right? So now what I am doing is nothing but, I know that current is defined as a rate of flow charge, right? I is equal to q by t. di is nothing but dq by dt. So what is dq? Can it be written as di into dt, right? So I'll replace it here. What I'll get here, if you see, di into dt is equal to rho into ds into dv, right? So what is this one? If I want only di, what I'll get here, rho into ds into dl into by dt. You know this one. What is this one? This is velocity, right? So now this, my expression is di is equal to rho into ds into v, which is velocity. Okay, so this current density, now I am defining current density. So what is the expression which I have got now? Di is equal to rho into ds into velocity, right? I will define current density as the current per surface area. Okay, di by ds, I will represent it as current density with units of ampere per meter square. So what I will get, it is rho into v bar. This is a vector current density and its value is rho into v bar, or you can use it di by ds. Okay, so finally, current elements. We have seen charge elements, right? Charge element is represented by dq, right? Similarly, current elements. Current element is represented by di into dm, or in other terms, I into dm. Okay, current and what is amount of length, okay, through which the charge has moved, I into dm. So I can write this one. If I take it as di as dq into dt, sorry, dq by dt. So what I can write? I can write it as dq into dl by dt will become v. isn't it? Or otherwise I can write it as di, I can write it as j into ds, right? So in this case, what is my expression? J into ds. So in either of these three ways, current element can be represented. Now we will come back to the magnetic force. We know that magnetic force is nothing but dF is equal to dq into v bar cross v bar. And we have seen in the previous slide that this is also is another representation of current element. So I am replacing it this one with di into df. Okay. Or I can write it as, if I take the full current, I will write it as IDL cross V. Okay. This is the force on the current elements, which is given by dF is equal to IDL cross V. In other words, what I can write it as flux density is nothing but dF by IDL. If I want flux is nothing but integration of B over the entire surface area, integral of over the surface area, dF by IDL into ds. Okay. So these are the different ways of how to determine the magnetic flux or force on the current element like this. Okay. I hope now you are able to understand the concept of magnetic field, magnetic force, and how to utilize these expressions for determining the force on the differential current elements. Okay. So we will see the problems in the next class along with Biot-Savart's law, which is one of the important law in magnetic fields. Thank you. And these are the lecture level questions. Go through them. These are uploaded in your coursework. Thank you. We'll meet again tomorrow.